Okay, we welcome all of you to attend this short course in the September series, which is about enhanced oil recovery as main topic or general topic. So since we have attendees from Latin America, we have to speak all in English. However, during the lecture, or we will provide like 30 minutes for a question and answer session. You may ask in Arabic, then we will translate and the speaker will respond in English. Also, you may write your questions in the chat during the lecture. Then the speaker will read at the end and answer one by one. So at the beginning, I will give an introduction about our activities. So our activities are led by the SPE Basra Section, the Society of Petroleum Engineers, local section in Basra, along with the Adaptive GeoEnergy Research Center in Basra as well. So I'm Wathiq Al-Muzaffar. A brief biography about me: I have bachelor's and master's degree in petroleum engineering from Baghdad University in 2002 and 2006. Then I got PhD in petroleum engineering as well from Louisiana State University in 2016 with 2 PhD minors in geology and applied statistics. Then I did a research as postdoctoral researcher at the Louisiana State University in the topics of reservoir characterization and enhanced oil recovery modeling. After that, 1 year visiting scholar at the University of Texas at Austin for 1 year about unconventional reservoir modeling. So about the AGRC, the Adaptive GeoEnergy Research Center, it's a non-profit research and training center that has been established in 2018. It was mainly in Houston, Texas. So all our services are being presenting mainly to the oil and gas community, specifically to the SPE community in Iraq. It provides high quality research training and consulting services in different disciplines in the geology, geoscience, and petroleum engineering. Our team have high-level technology, present high-level technology breakthroughs in these topics. Our teams mainly from Iraq and United States. The main office here in Basra. Here are the information regarding the website, emails, and the address. I want to give some introduction about the essential references for petroleum engineers and geoscientists, because we have been receiving many questions how to search for the information either for students, postgraduate students, and for the researchers. So the main reference, the Society of Petroleum Engineers, that offers 2 main references. One of them, PetroWiki, which is free of charge, that present for everybody an essays in different topics in the petroleum engineering. Also, there is one Petro that has more than 200,000 papers in different topics in the petroleum engineering. The same thing for the AABG. There is AABG Wiki. Also, there is database of the AABG that you can get information about all the oil and gas field worldwide. There is SegWiki from the Society of Exploration Geophysicists. It has the same idea of PetroWiki. Also, there is EarthDoc from the European Association of Geoscientists and Engineers. EarthDoc, it has all the papers that have been presented at the EAGE conferences, as well as 3 or some a few journals that led by the EAGE. There is also ResearchGate. You can get a free account on ResearchGate. You can also follow many researchers, whatever researcher you want in many different disciplines. Then you will be involved to many solutions to any problem that you are working on it. There are some journals that are free to download, like Journal of Petroleum Exploration and Production Technology. All the paper of this journal can be downloaded like free. Also, there are some other journals from the MDPI, the Switzerland Publication Office. They have 2 journals in petroleum engineering, geoscience, and energies. Both of them offer open source or open access journal papers. So these are the main or essential references for petroleum engineering. So one of the main or recent activities for the AGRCE and the SPE Basra section is to deliver short online courses, like net of 3 hours, total of 4 hours, presented in one day. So our short course today, it's about the rock fluid interactions and their role to enhance the recovery of oil. Our speaker is Dr. Santiago Drexler, that has bachelor's degree in chemical engineering from the University of Buenos Aires in Argentina. After that, he goes master's degree at the chemical EOR from the University of Oklahoma in the United States. Then got his PhD in reservoir engineering from the Federal University of Rio de Janeiro, Brazil. He started in the oil and gas industry, working in projects of chemical EOR and water flooding. In addition, he worked in the setup and the implementation of the lab specialized for the CO2 EOR and WAG for Brazilian carbonate reservoirs. Dr. Santiago has worked both in academia, the University of Oklahoma and the Federal University of Rio de Janeiro, and some other international companies such as Petrobras and Halliburton. He was also a visiting professor in the petroleum engineering of the Federal University of Rio de Janeiro for 6 years. He's currently a principal reservoir engineer and dev team leader at Halliburton, Brazil, working in the area of formation evaluation and digital technologies for reservoir modeling. So, Dr. Santiago, if you hear me, I think you will be able to share your presentation now.
Yes. Can you hear me okay?
I hear your voice is a little bit slow.
Okay. Let me know if it gets any better. I will try to. Hello?
Hello?
Yes, can you hear me?
Yes.
Okay. Let me share my screen then. Can you see the screen?
Yes.
Okay, I can try to start my video, but then if the connection gets slower, let me know and I will turn it off.
Okay.
Okay. So I'll start the presentation. So thank you very much for this introduction, Dr. Watek. My name is Santiago. I work at Halliburton at the in-grain service line in modeling. You actually had a talk with William, he's my colleague there a few weeks ago. So the idea today is to not to talk specifically about modeling and the digital workflows. It's more about talking some fundamentals and mixing up some simulations with experimental ideas. Basically, and how do we will go ahead. We have two sessions. So for the first, like introduction, since we are having backgrounds and different how deep to go. So I decided more deeper.
I think there is noise coming from you once you start talking.
Okay, let's go ahead and start with the presentation. So if you have any connection problems or you hear any noise, please let me know so I can try to fix it.
Okay.
So we'll start with the safety moment, as it's as our culture at Halliburton. This is not a Halliburton presentation specifically, but we will do this a brief safety moment, and the idea here is to focus on coronavirus, and coronavirus pandemic is through all the world. And I wanted to try to give a kind of a different message. We all know already how we have to take care of ourselves, what's the dangers of this disease, and some prevention measures we have to take. But I wanted to focus particularly in how to support our loved ones, and I think it's very important to be kind to people, even if it's family, friends, colleagues, and other people we interact with. We need to be empathetic, and we need to be understanding, checking with people we love, and encourage people to do activities they like, and also try to see how to deal with anxieties, and specifically with older people and with children. It's very important that we keep this in mind. It's a very hard situation for most of the people in the world, so I think it's an important message to share. So to talk about our agenda, as I said, we had two different blocks. And in the beginning, the first part, we would things about our recovery, and then aesthetic properties and dynamic properties. So it's more a review of concepts that we need to introduce in order to talk about a little deeper into rock fluid interactions. And then for the second part, we will talk about rock fluid interactions, basically go more in depth into wettability, and then some case studies that most of them will be focused on Brazilian reservoirs. So let's go ahead and start with the first part of the introduction. So this is a pretty basic graph that most people who has taken a reservoir engineering course has seen about phases in development of a field. Basically, after exploration and appraisal, geological model, we have the production phase, and we have primary recovery and secondary recovery, and in many cases after that, tertiary recovery. And the idea is try to understand what involves each of these phases, and why do we research and investigate enhanced oil recovery as something that is so important in most cases, even when it's not applied in many reservoirs. But it's important to know how to evaluate this and how to understand this. And we will see that rock fluid interactions play a very important role whenever designing an EOR, even if it's a CO2 injection or if it's a surfactant polymers injection. We need to know how to characterize rock fluid interactions. So just to start with the definitions, I took the SPE glossary for exploration production, and we can see that for improved recovery, this is basically a combination of methods in order to enhance the recovery techniques, and this includes EOR and other methods that try to enhance the flow of the hydrocarbons towards the wellbore. And then for the phases of recovery, we have the primary recovery, that is without any injected fluid for pressure support. So it's the natural energy from the reservoir. And then secondary recovery, basically water flooding or gas flooding for pressure support, maintenance. And then enhanced recovery, the variety of processes that seek to improve the recovery. And it doesn't really specify what. So we can go and see some other definitions that are a little more specific. Like for example, if we take Carquana from 2002, we can get the main objectives of EOR, reducing the mobility ratio to improve the sweep efficiency. And the second objective is to reduce capillary and interfacial forces or to eliminate them. And then it could be a combination of both of them. So these are the main goals when we are seeking for EOR processes. So we will come back to this specifically in the second part when we start talking about how wettability affects all this. And then lastly, I put this from Sutter in 2008. I put this definition because I think it's important to distinguish that mostly when we talk about EOR, we are talking about injecting external sources of energy or materials in order to enhance the recovery or to improve the recovery. So that's with all that, if we mix all that together, we can get to the final idea or definition that includes the 5 main EOR techniques that can be chemical, thermal, miscible, or microbiological. We are not going to go through this. If you are having this series of talks, I imagine that you will have talks about all of this. But it's just an overview of what is mainly understood as the EOR processes for oil and gas. And then now we're going to go back to the definitions that we need to use. And first we will start with the type of rocks and reservoir rocks. So we don't really need a lot of details, but we know that mainly we separate the type of reservoirs into 2 main types: the clastics formed from pre-existing rocks by erosion, transformation, depositions, and are basically the sandstones, shales, and sands. And then we have the carbonates, and a lot of examples I'm going to give it are from carbonates in this case, because most of our research in Brazil is focused on pre-salt reservoirs that are carbonate. So carbonates are formed from organic constituents and chemical precipitates. So we have an organic and inorganic source. And then they include mainly dolomites, limestone, chalks, and others. And they are very different, and we will see that regarding the rock fluid interactions. So it's really important to know how to understand mainly what type of rock we have and how it behaves in order to try to model wettability and try to model how fluids will displace in the rock. So porosity, as most people here know, is basically the volume of pore spaces in the rock divided by the bulk volume, and it represents the storage capacity of the rock. And we have the total porosity that it will account for connected and non-connected pores. And we have the effective porosity that will give us the volume of interconnected pores. So it will be affected by the connectivity, and it will be the one that produces an effective porous network in which the fluids can displace. And then there is a classification regarding to at which phase of the rock formation the porosity was created, and this is important for fluid flow. And we have the primary porosity. It developed during the position of the rocks. So basically, it's the void spaces between the grains and the crystals. So this is usually the most organized and principal porosity that we see when we see a rock. And then there is a secondary porosity that it developed after the initial deposition due to different processes, mostly geological, geochemical, like for example, dissolution reactions, dolomitization, and other reactions that could open channels or closed channels depending on what type of process happened during the time. So what is important, this could enhance the quality of the rock, but in most cases it could also decrease the quality of the rock, because this type of porosity will increase the heterogeneity of the rock, and then it will be harder to have a homogeneous or displacement front whenever we have this heterogeneity and preferential paths and then closed systems. And then also in the classifications, we have also to talk about the cutoff porosity. That is a very important value because it's usually determined to identify when we have production regions within a formation. So there is no magic number. Usually a number that is logical could be around 5%, but this will depend for each type of asset and for each type of operation conditions. So obviously we cannot generalize that we will cut off the same porosity for in any depth of reservoir, or any rock type, or any type of operation, any conditions, economical conditions of the projects and type of reserves that we have. But then it's important just to say that this is required in order to specify the net pay, that it will be the part of the reservoir that we can produce commercially. And then with this, we will have the net to growth thickness that will give us the fractions of the reservoir in which we have interest commercially, and then the fractions of the reservoir or the fractions of the formation that won't be considered reservoir in commercial terms. Okay, so talking about determination of porosity, the routine core analysis is the most accepted way. So basically, we need to obtain plug, sidewall cores, or any type of samples, rock samples from the formation in order to physically measure porosity in any of the accepted ways in the industry. And there are standard procedures detailed in the API recommended practices. Some things that I just wanted to comment that are very important to take into account is that even if the procedure is very simple for measuring porosity, particular care should be taken during the coring procedure and cleaning and preparation of the core for measurement. That is, when we remove the core during coring and plugging of the core samples, we need to make sure that we avoid mechanical damages, even when the core is being removed from the formation, but also when we are plugging the formation, the core. So mechanical damage will come damage permanently the core, so the plug that we cannot use it for anything then. But then also it can create fake permeability and porosity, or we can close permeability and porosity, and we can actually measure something that is not representative. So coring is a very important part. Also, care should be taken when cleaning the cores for measurements, and that is because we can form chemical damage by, for example, precipitation, if we don't use the right procedures depending for each type of fluids and formations and rock that we have in the formation. So basically, in the routine core analysis, when we do together in the poro per measurement equipment, we will do permeability and porosity together. But then there are also different type of apparatus when we have, for example, different sizes of samples that we cannot put inside the core holder. And for that, we can use an equipment that is a helium per volume based on the Boyle's law. That is also very simple, but we need to have a control atmosphere in order to know particularly how to calculate the gases, how to relate the gases pressure to to the mole number. So we need to have a very controlled temperature in the lab and a way to control the pressure. And then also we can use a digital rock analysis. I think that William presented some part of this. I will present in the end some examples of this also, that mostly can be used for quality control, because since we can represent the rocks and then we can simulate flow in the porous systems, we can also calculate porosity and permeability, and we can use this as a very fast calculation in order to quality control both the digital and the physical workflows. And then if we go to a log scale, we can use the density log data to calculate porosity. And this is a very, very basic petrophysics knowledge, right? Because for the density log, if we know the density of the matrix and we know the density of the fluids, we can estimate the porosity directly from the logging. And then what the difference is, what the difficulty can be is when we have lithologies variations and we don't know really how to classify this. And then in that case, we cannot use these single values, and then we need to complement this with any other logging tool to get more information about how to estimate a realistic porosity. And for that, we can use, for example, the neutron porosity logging tool that can also give us information regarding porosity, and then combining the density and neutron logs, we can get interpretation of the lithological and fluid changes in the formation. So we can get, for example, when we get differences between them, we can know that there's differences in the matrix that we use for calculation in porosity, and then we can try to get information for the matrix, and then we can see that we can have gas, for example, in the pore space, or we can have shales or clays that will affect the response of the tool. So then basically petrophysicists uses the separation and the crossover to do a complementary analysis and get more information to do this characterization. So now going to something that is a little more interesting is permeability. It's basically capability of transmittability of the fluid for by the rock when it's completely saturated with only one fluid and is submitted to certain driving force. That is, in our case, is mostly the pressure difference across both ends of the rock. And then with that, permeability will represent how much of the fluid can flow for a certain driving force or a certain delta P that we have across the rock. So you can expect that this is very important, right, in reservoir characterizations, because it will define what are the production rates and when we are building a reservoir model. So it's basically porosity is storage capacity and permeability is production capacity, and both of them, a great effort is done when doing rock typing in order to correlate both of them, because together they will give us the quality of the rock, right? So when we want to characterize this, is when building a model, it's very important to be able to characterize storage and reserves and also production. So now we'll talk a little bit about this permeability. So basically, it's a little more complex the way it's affected than porosity, because it will not only depend on how much void space we have, and not only depends on how much it is connected, but also will be affected by pore throat size distributions and the pore radius distributions, and also by cementation, tortuosity that we have, and the pore shapes. Type of mineralogy, and then if we have secondary porosity. So all of this will affect how well or how bad the fluid will flow across a sample of rock when we have a delta P. And then if we are talking about permeability, we need to start by talking about the experiments by Darcy, and then we can have, it was this obtained for flow in sandbags, sand columns, but then it was extended for groundwater and other type of subterranean flow, and then for reservoirs, oil and gas reservoirs, it was adapted in a multi-phase flow way, as we will see in the last part of this talk. But then when we are talking about the Darcy's law, we know that the flow rate will be proportional to the hydraulic head, what we call. That is mainly in the case of flow, it will be, the driving force will be difference in height, difference in pressure. So this differential will be the driving force for the flow. So that's the terms H1 minus H2 divided by L there. And then we have a constant of proportionality for this medium that will be the hydraulic conductivity, and then the cross section. So basically, when we are doing calculations of flow inside the reservoir and we divide this in cells, we are interested in the velocity. So the definition of the Darcy velocity will be the flow rate divided by the cross-sectional area. And if we extend this, we will see that if we use also the fluid viscosity, we will see that the constant of proportionality there is what we call the permeability of the porous medium, and it's basically a property of the rock. So it shouldn't be affected by the rock fluid interactions. We'll see that we have some experimental issues there, but basically, since the medium is saturated 100% with only one phase, it is a property of the porous medium itself. And then I just added there, if we solve this for horizontal linear flow, we have this direct relationship between permeability, flow rate, viscosity, and the driving force, that is the delta P over L, and then the cross-sectional area. Of course, that if we use different geometries, like for example, how to calculate the flow inside the wellbore, and we use the radial coordinates, we will get a different expression that relates the flow rate and the delta P in terms of the permeability. So as I was saying before, we have the absolute permeability is a property of the rock, and it represents the single phase flow conditions. So it shouldn't be affected by the type of fluid that we have. But when we have measurements using gas, we can see that the experiments, they will retrieve higher permeability values than those using for the liquid permeability. And this shouldn't be a condition, because when we enter permeabilities in a reservoir model, we are not considering the permeability according to which phase is flowing over there. But the thing is that this is caused by what is called a slippage effect, that is basically observed in the gas flow rate, that they do not follow the no slippage condition. So this was characterized by Klinkenberg, and it's called the Klinkenberg effect. And it's usually should be corrected when we are doing measurements of permeability. So if we are doing gas measurements of permeability, we should account for the Klinkenberg effect. And now we'll see a little bit about how it is. So basically, the quantification of the Klinkenberg effect, we have the relationship between the brine permeability or the liquid permeability and the gas permeability. And it depends on the mean pressure, that will be the mean of the pressures, inlet and outlet pressure in the experiments, and a constant C. And we can easily get this factor C by performing the measurements at different mean pressures, and then we can extrapolate to the zero of mean pressure, in which we will get the permeability if we were measuring with the liquid. So basically, if we have different sets of pressures and we do a straight line approximation and we extrapolate, we can get the equivalent liquid permeability. So let's see a little bit about how we can measure the permeability. So we usually do this, as I was saying before, in part of the routine core analysis, and then we have a series of plugs and or sidewall cores, and we know the depth of the plugs. And basically, when we do this routine core analysis, what we will end up having is a K and phi data set, large data set, depending on the number of plugs on sidewall cores that we have in terms of depth. And the idea of this is that we will characterize permeability, porosity, and try to group them in what we call the rock types, right? So we will create the clouds into semi-log data of K and phi, and we'll try to group them in different, by different techniques. We can use the FZI, or we can use Winland, or different criteria to define which are our rock types, and also classify which are the high quality rock types and low quality rock types, in order to be able to create a model and see how they are distributed in the reservoir. So we have a standard for permeability determination in the API recommended practice 40, also as the same as for porosity. And usually when we have a complete set of routine core analysis and combined with a special core analysis, we will perform both. We will do the Klinkenberg corrected gas permeability using a poroperm as a common practice. And then also we can get brine permeability either in core flooding experiment as part of SCAL when starting SCAL, or also we can do that separately in a simpler setup when we can just measure the delta P and flow rate and then calculate the brine permeability. So for steady state measurements, that is the most common one for permeability. We basically have a controlled gas flow rate and pressure, and we have two gas reservoirs, an inlet, an upstream and downstream, or inlet and outlet, and we have valves in order to control, to regulate this, how much flow we will allow to pass, and basically we will measure the different pressure differential in the inlet and in the outlet, and we will have a confinement pressure, right? Because we need to measure this under confinement that is exerted by an external. We have the rock sample inside the inside the cell, and then we will have a pump injecting the confinement pressure in an outer cell. So with this, it's a very simple setup, and it's not a very long experiment, but it depending on the type of rock that we have, if it's homogeneous or heterogeneous, and basically if it's very tight and if it has a very low permeability, we will have it can take a very long time in order to get the steady state measurements. So this can be a problem for some type of complex rocks, and basically when we have a very tight rocks. And also, as I was saying, a part of routines can be the liquid permeability is usually measured, and this is pretty straightforward, because when we have a core flooding setup, usually we have a way to measure the pressure differential across the core accurately, and we have a pump that controls the rate with a high precision. So usually it's not, it's very straightforward to have sets of flow rate and delta P. Then I wanted to explain a very overview of another unsteady state, and that, as I was saying, when we have a very tight samples, ultra tight samples, and we cannot perform steady state measurements, there is a pulse decay technique that is also interesting, because in this we won't measure the steady state delta P and relate it using the Darcy equation to the permeability. What we will do, we will inject an upstream pressure pulse, and then we will measure the response of the sample throughout the time, and solving equations that are related to the momentum balance. We can get a relationship in time for different pulses. We can get a relationship of the pressure decay and how to infer the permeability. So I didn't want to go into a lot of detail about this. I had added in the beginning all the derivation of this, but then I thought it's not really the point of the talk, and I would take a lot of time explaining this. So basically, I just added here just to see what type of analysis is carried out. So basically, we solved the momentum balance for compressible and steady state flow in terms of the pseudo dimensional pressure. And then after deriving this, we can see there in the slide that it's we can approximate this as a straight line in a semi-log plot between the dimensionless pseudo pressure and time. And if we know the porosity of the plug sample, we can perform these straight lines and calculate the permeability and at the different pulses. And then, well, we can have at the log scale, we can have permeability inferred mostly indirectly. So we can use if we have the density log data we said before, we can use the Coates equation in order to relate the permeability to porosity and the connate water saturation or reducible water saturation. The thing is that, well, we need to know the SWI to apply this, and also that this equation was derived mostly for sandstones. So if we have a heterogeneous complex reservoir, there are some limitations. So when you use this type of equation, you need to know that you are really assuming some type of behavior for the rock. So it's not always so straightforward as applying the equation and getting one parameter from the other. And then there is also NMR logs and resistivity logs that can be used to infer the permeability indirectly. So basically for the NMRs, you need to know the clay-bound water also, and the total porosity and the capillary water. And then for the resistivity logs, you need to do experiments in order to make correlations between formation factor, saturation exponent, and porosity and permeability. And also going for the reservoir scale, we have well tests. So I'm just explaining all these different steps just to emphasize how important is the scaling thing, because when we are talking about a very homogeneous formation, we don't have these upscaling effects. But when we go to complex reservoirs, sometimes it's very hard to come from data that we have from plugs, or even if we are going to talk about digital rock analysis or pore scale, then plug scale, and then core scale, and then how to input this into a field. So I'm just trying to say what different ways we have to relate all this data at the different scales, and then upscaling techniques are really important in order to create a good model of the reservoir. So at the reservoir scale, we have well tests, so pressure transient analysis, and then build up and draw down rate and pressure data. We well testing that data analysis that we usually do in commercial software. We can estimate permeability at the different zones, and also we can include heterogeneities using inverse solutions. So I put that reference if anyone wants to check this type of procedures. And then finally, talking about the permeability determination, we can also use digital rock analysis, as I was explaining about how we can use the digital rock analysis for porosity calculation. We can use digital rock analysis for permeability calculations also. And this is mostly used for QC because it's not a main way to to calculate your permeability or porosity, basically the preferred way is always routine core analysis, but we can count on DRA for fast response and for quality control of the analysis we are performing. So basically the procedure is we will scan the cores samples using a medical CT resolution that is around 400 micrometers per voxel. And then in this resolution, we will select the textural groups. Basically, geologists will analyze the whole core of the well, and then it will classify this into textural groups, and then we will select plug samples to represent each type of textural group. And these selected plugs will be taken from micro CT scan that will be higher resolution scan. So when we go with the selected plug, we will use a micro CT, and we will start at the 40 microns per voxel. And then at this resolution, we will be able to identify flow systems in the rock. And basically, this is qualitatively done by geologists also. And the idea here is to understand regions of the plug and how many subsamples we need to represent the flow system in the plug. So when we identify the subsamples, depending on the resolution, we will have to actually trim a very small subsample from the plug, and then we will scan high resolutions that can go depending on the MICP or the pore size distribution. We will actually know how far we have to go in resolution, and basically we can go as far as 0.5 microns. That will capture actually up to nanometers or pores lower than a micrometer. And with that, we can make sure that we will capture the dominant flow system, and then we will have to integrate all of this into with a upscaling technique into the plug, and then we can simulate the flow at the different scales and then at the plug scale, and we can use this as a way to validate our physical measurements for QC. So this is just an example because just to show, because it's not a lot of people know how this. I know that William presented this before, but maybe some other people weren't there. And since this is not such a traditional workflow in the industry, I think it's a good idea just to show some examples of how it works. So basically, we see on the left, we can see the region of the whole core where the plug is taken, and then we can see the scan of the plug at the 40 microns per voxel, and we can see the two subsamples showing different textural groups or different flowing units, and how digital MICP is acquired when we resolve the porosity. So it will give us a pore throw size distribution, and we can compare that with the physical MICP. And also we can get capillary pressures that we will talk a little further in this talk from digitally also. But here I'm more focusing in the RCal workflow. So basically this is just to show the cycle of how we can use the whole core scan, and the dual energy CT scanning will help us to give us core logs, that is density and PE logs for the scan core, and then plug selection. And then after plug selection, we can do scanning of these plugs, and then all these plugs also will go through routine core analysis, and then at the same time we do subsample selection and high resolution scanning, and then we will do quality control and integration between the conventional core analysis, routine core analysis, and the digital core analysis, and we will match the results. And this digital workflow not only will give us faster results, but also will support us in creating the rock types, as we will see in the following slides. So this is another example of the routine core analysis by supported by digital rock analysis. In this case, we had three different rock types or textures. They were the green one was dominated, and the flow was dominated by the grains. And then we have the red one. We have a mix, what was called a mixed texture, in which we had the grains and the mud dominating. And then the muddy texture, that is the blue one, we had the mud dominating. And so we can see that depending on the concentration, the amount of micrate it has, and how the grain size will affect the absolute permeability of these rocks. And we can see also thin sections over there in which we can see the very different structures of the different textures, and then how they sort porosity and permeability together into the same plot. And basically for the routine core analysis and the digital rock together, we could make a classification of the rocks in a textural basis. And since we know how the textures are distributed throughout the whole core, we can take these classifications into depth, and then we can do rock quality, as we can see in the rock typing example there, classify in a combination of textural analysis together with the routine core analysis. And we can also see how digital rock analysis represented the pore throat radius size distributions for the three textures, so we can actually understand how the changes in the diagenetic effects, like for example the effects of in the absolute permeability with respect to the pore throat size distribution, how we can understand this in a textual basis and take all this information to build a more robust model. So just summing up a little bit about the digital rock analysis contribution to routine core analysis. Some of the advantages here are that we can aid in plug selection. So we can provide virtual plugs. We can provide ways to analyze and see the plugs before actually taking them out of the core and doing any experiments on them. So we can actually predict if the plug will fail, or if the plug will have issues in the measurement, or if the plug will or not will be representative. Because sometimes when we do selections just using an average distance in plugging, we can see that then the selected points, sometimes they take half of a texture and half of the other, or they have such heterogeneities that they won't represent any rock type. So they will be basically useless when we want to use them to create a model. So we will be able to see that, and also we will be able to measure, to give an estimation in plugs that can be very challenging for physical measurements. And also they will be good and give us an idea of how to identify the REV and the contribution to flow of different pore systems. Like for example, we can try to understand the contributions of the fractures in the fracture plugs on some type of developments that are really over the edge of routine core analysis. And then also we can use the digital rock analysis to QC and to provide faster results in order to be able to use some of the results before the whole ARCAL program is finished. Okay, so now talking about the dynamic properties. So at this point, these properties are more complex because we will have to take into account in the interaction between fluids and interactions between the rock and the fluid. So all the previous, what we call the static properties, are used to build the geological model, and basically the static model. And we needed to give all this introduction in order to start talking about these properties that are a little bit, more complex properties. So we'll start with interfacial tension. It's a very important characteristic in the capillary effects of the reservoirs. So interfacial tension is basically the force per unit of length or the energy per unit of area of the interface, basically. And the idea here is that whenever we have an immiscible, two immiscible phases, and we have an interface, the molecules at the interface will have an excess energy when compared to the bulk molecules, and that is basically caused by the intermolecular forces. As we can see, and it is a very, very simple figure, but it explains very well the process, because we can see the bulk molecule is pulled in all directions by the same internal molecules. So all the neighbors are the same. And when we take a surface molecule, we have the action of a net force that is the interfacial tension, because the forces are not balanced in the same in all the directions with the same magnitude, right? So we can see that over one side of the magnitude, they will interact with different type of molecules from a different phase that on the other side of the interface. So of course that I am not going to go deep or explaining into chemical intermolecular forces, but everybody understands that the more similar the molecules are among themselves, the more ways they have to interact with each other. So they will have a greater energy of interaction. So in this case, we expect that for the both phases, the molecule will interact greater with the molecules alike in the same phase, and with the other molecules, it will have a low interaction. So that's what causes this balance of forces. So, as having said that, the more different the molecules are among themselves, the greater the IFT will be. And that is because if we see this equation, simplification equation that we have on the bottom, we can see that there is actually three contributions for the interfacial tensions. That is the sum of the interactions between the molecules on the A molecules, or the A phase molecules, and the interactions of the B phase molecules with each other, within themselves. And then we have the energy of interaction, 2 times the energy of interactions between molecules in the A and the B phases, right? So the more similar these two A and B molecules are, the greater this term will be, and the lower the IFT. So when we have a very polar solvent, like for example water, and a very non-polar phase, we will tend to have a greater interface. And if you had any talks about surfactants, uses of surfactants, is the whole idea of surfactants is reducing this by having a part of the molecule that is similar to the polar phase, the water, and then a part of the molecule that is similar to the non-polar phase. And then we have an extreme cases when we have miscibility. And then in that case, the phases are so similar that the interfaces fades. The interface will fade, and then we have an IFT of 0 when the molecules are similar enough in order to be miscible and form only one phase. So, okay, this is interesting, but when we are talking about reservoirs, what do we want to know about this? Well, basically we have water, brine is a polar phase, and then we have hydrocarbons, and then oil. If we talk about hydrocarbons and we talk about paraffins, we will say that oil is a non-polar solvent, a non-polar phase, and mostly, but then oil can have polar molecules in it, and basically the asphaltene and resin parts of the oil are the ones that have this polarity and that will interact greater with the aqueous phase. So that is when it gets a little more complex regarding interactions, because oil is not all the same. It will depend on the SARA analysis or the distribution of saturates, aromatic asphaltenes, and resins. So we'll talk more about that later. And then usually gas, we can consider the gas phase as a phase that will interact very weakly with all the other phases. So having remembering capillary rise, and this is a high school experiment, but then we use the concepts in this to understand capillarity in the reservoir. So it's useful to understand that at the interface, if we have the balance between the gravity and the interfacial tension forces. So if we have this, if we take a capillary tube, we put it when we immerse it partially into a recipient with water, we will see the capillary rise, and we will have this scheme similar to that on the right. And then if we take the air-water interface, that is the 1 and 2 interface, we see the curvature of the interface that will be represented by the capillary pressure that we will explain a little further. But now what we have to know is that this is basically this, at this interface, we have this balance between the two forces, and it's represented by the interfacial tension, what is called the force up there, and the gravity forces that is caused by the difference in the weight in the columns that we have in the air column and the water column, as we see in the force down. So basically, if we balance these two forces, we get this equation that will give us the equation for the capillary rise, that will give us the height of the meniscus at the elevation of the liquid. But why are we trying to talk about this? What's the importance of this? Well, we can take this to the water oil system, and then if we assume that the porous medium will be a set of parallel capillary tubes of different radius, because we have different pore radius, we can use this type of model, simple model, to understand how interfacial tension will relate with the capillary pressure, or the pressure difference across the interface. So that's what we're going to talk about now. So basically, capillary pressure is the pressure difference across the interface. So we can see from this previous image, we can see that we have a curvature of the interface, and that is saying to us that we have a pressure difference, and actually the pressure at 1 should be higher than the pressure at 2. So we can see actually 1 kind of pushing the interface downwards. So when we have water and oil, for example, in the reservoir, we have the same phenomena. But then in the reservoirs, we usually define the capillary pressure as the pressure of the non-wetting phase. That will be the guy here, the 1. So it's usually greater. And then we will have the pressure, and then it will be the pressure of the non-wetting phase minus the pressure of the wetting phase. And that is because usually with this definition, we will get a positive value. And then, as you can expect, this difference of pressure will be, as we saw before, it will be basically a function of the interfacial tension. It will be a function of the wettability and a function of the pore radius. You can intuitively, everybody knows that if we have a very large recipient with a large radius, we don't see the same capillary effects in the meniscus as we will see in a capillary tube. So just coming back to this, if we come back to this drawing and we use the capillary pressure definition of the difference of pressure in 1 and 2, and then we use the hydrostatic pressure in the water column inside, and then the hydrostatic pressure in the air column inside the capillary tube, we can have we can add everything up, and then we can get an expression of the capillary pressure in terms of the height of the meniscus. So we are not, this is basically really useful to determine in terms of capillary pressure, how to relate the capillary pressure with saturation distribution when we have capillary pressure curves. We are not really going to talk about this application because it's not really in the scope. I was just using this example in order to get to this equation. So if we replace the equation that we had before, we get to this very simple equation, but it's a way that to relate the capillary pressure to the main terms that we are interested in. For example, oil-water interfacial tension, the contact angle that we will be seeing a little bit that is related to wettability, and the radius. So we can see that the smaller the pore radius, the higher the capillary pressure. So that says us basically that we need to exert a greater pressure difference in order to invade the smaller pores. So that's a very important fact when we are trying to characterize the capillary forces and we are trying to characterize fluid distributions. And then also it tells us that it will be proportional to the oil-water interfacial tension. So basically, the greater the interfacial tension, the harder it is to overcome this capillary pressure. So we have small pores, and then we have high interfacial tension as the cases that will be harder. And then when we have a fully non-water phase, like for example, when we have gas, this tends to be higher. And then when here we can actually see why the use of surfactants will be a way to improve wall recovery. When we see that we need to decrease the interfacial tension, and if we decrease the interfacial tension, we will decrease the capillary force, and we will easier displace the oil from smaller pores. But in the second part of this course, we will talk about this recovery in more details. So now focusing on how we can measure the capillary pressure. So capillary pressure, there is one standard procedure is the porous plate, and the porous plate has a semi-permeable membrane that will allow a selective pass of one of the phases. So with this, it's just a chamber in which we will increase the pressure in steps. So if we start with for example, the core saturated with water, and then we inject a phase, in this case air, as in this design, but in gas phase, we will increase the pressure in steps, and we will see how much fluid, how much water is displaced from the core. So then if we reach equilibrium at each step, and we don't allow any further recovery, we don't have any further recovery after reaching equilibrium for each step, the idea is that we will end up having a relationship between the pressure that we put that is equivalent to the entry pressure or pressure difference and the saturation. If we do a mass balance and we know the volume of the rock, and then or we weigh the rock and we do it for weight difference, and we know the density of the fluid, we can get an idea of the saturation, and then we can get a relationship between the pressure, the capillary pressure, and the saturation. And then we can see that basically we have, it's here below, I don't know if you can see, but here we have the first value. That is basically what we call the entry pressure. That is the minimum pressure we need to have to get any displacement from the core. So basically this is, we observe this type of entry pressure when we are forcing a fluid that is not wetting fluid, and we need to overcome this initial pressure in order to get a part of the non-wetting fluid inside the core of the ply and displace some part of the wetting fluid. So basically, as we see here is a drainage curve. Here we have the water saturation. So I'm sorry, we have this bar here that we cannot see, but we have the water saturation here on the x-axis and the capillary pressure. So we can see this curve goes from the totally saturated plug with brine, and it decreases the water saturation until reaching this asymptote value that it corresponds to the connect water saturation. So here we can get very high capillary pressures, and we can see that we won't displace any more water. That means that this water is irreducible water, and we cannot, even if we increase the capillary pressure to
highest achievable value, we won't be able, with this interfacial tension that the fluids have, we won't be able to get any more displacement. And then we have another very common in the industry method is the centrifuge capillary pressure measurement. So basically here we will relate the centrifugal force to the capillary pressure because when we have the rotation effects, we will have a potential field as that it can be related to the force field caused by the capillary pressure. And then if we have a way to relate this in terms of the geometrical parameters of the centrifuge, we will know what is equivalent between the speed of rotation and the capillary pressure. And then if we know how much fluid is displaced and at each equilibrium stage for each rotation, we can relate the saturation with the capillary pressure. Okay, so the idea here is not to go into a lot of detail about this, but I just want to say that it's not so straightforward because it will be easy to collect the amount of fluid that was displaced and just use only the formula to relate their speed of rotation to capillary pressure and do the plot. But then we have some issues or some more difficulties that, as you can see in that figure there, we have a saturation distribution across the plug. So we don't have we have a very hard time in knowing the average saturation distribution for each speed of rotation. So we cannot use just a balance to know how the saturation is distributed in between the inlet phase and the outlet phase. So there are a lot of methods. I will just describe the names of them, and then there are a lot of references that explain the different methods that you can use to convert the data produced by the experiment and some parameters that you take in the experiment into capillary pressure, average saturation, or inlet phase saturation measurements. So another equipment, it's really recommended to use new generation equipments that will provide automatic reading of the fluid and automatic spinning rotation adjustment for the whole cycle. So with that, you really improve the precision of the experiment, and you will be able to analyze the volume of fluid displaced with the speed of rotation and time in a more accurate way. So going back to the very basic development of this technique, this is the relationship between, we use the density difference between the fluids, the speed of rotation, and the radius, a variable radius, because the capillary pressure will be variable within the radius of the sum of the distance to the axis of the equipment. And then we have a way to average the saturation in the whole plug. And then to resolve this, as I said before, we have relationships between the average saturation and the radius, the maximum and minimum radius in the distances from the inlet and outlet of the phase, and the capillary pressure. And there are some calculation methods. The Hassler and Brunner was the initial one, the most basic one, and then there are a lot of modifications that improve the methodology, and there are still new methods, and labs develop their own methods to do the data analysis. So this is not something that is a unique standard procedure. It's like, for example, a score frauding. Each laboratory or each institute will follow the recommended practices in order to treat the data and produce the better result from the data that they can. So just a summary of the procedure. We have the increase in the rotational speed in steps. So for example, one example is to increase in 250 RPM steps and then measure the volume of fluid at each step. So the idea here, and this is a very, very common experimental problem, is that we should take enough time, we should leave the equipment spinning for enough time to obtain a plateau in the produced volume at each step, because otherwise we won't be measuring the full fluid displacement. But this is sometimes people rush the experiments in order to, because they need to produce results, and then we have this type of course that are kind of incomplete, and we need to work with not such a high quality data. And you need to know the fluid's density, and then if you have the produced volume, then you can calculate a relationship between PC and the average saturation, and then the saturation at the phase. For the saturation at the phase, we need to use any analytical method that ones of I taught before, or there are many others that are newer than those. And then you can calculate experimental analytical data, and you can have a matching of the data for quality control. Then another technique that is very useful is the mercury injection capillary pressure. It's not basically not only for capillary pressure, so as we will see, but it's an interesting technique because we will use we will place the plug in a chamber. The plug, no, it's a portion of the plug, usually a wafer or a half a wafer of the plug into a chamber, and then we will inject mercury at each step at different pressures, and we will measure the mercury intrusion. So basically, mercury will invade the larger pores first, and then as we increase the pressure in different steps, it will get into the smaller pores. So this can, it usually works with two chambers, a low pressure and a high pressure chamber, and it can go up to very high pressures, reaching pores in the nanometer scale. So we can get up to 60,000 psi, and then it can get into very small pores. And then, since for the mercury air systems, all the physical parameters are really well known, as for example, the density, the interfacial tension, and the contact angles are very well known, because for the mercury air system, we can create a capillary pressure, a saturation curve for the experiment that it will relate the saturation of mercury to the capillary pressures. But then we need to convert this into the reservoir fluids data. And for that, we need to have wettability measurements for the oil and water system, oil water rock system. And also we need to have interfacial tension measurements for the oil and water system in order to convert the data from the MICP to reservoir fluids. So this is just an example, and basically this technique is very much more useful to obtain the pore and throat size distribution. So as we can see there, with the capillary pressure equation that we derived before, we can relate the capillary pressure to the pore radius. And if we know, for example, as we said, for the mercury, we know the IFT and we know the contact angle, we can get a relationship between saturation, the frequency, and the radius, or the normalized saturation and the radius of the pores. And with that, if we integrate that, we can get the cumulative pore volumes, or the cumulative number of fraction of pores in terms of pore size. And we can see, for example, in digital rock analysis, how far we need to go in resolution to represent the majority of the pores. And then on the right, we have an example of the capillary pressure from MICP compared with the digital rock analysis there. and convert it. If you can see, it says all prime because the data was already converted to reservoir fluids. Something important is to see the effects of permeability in capillary pressure. So usually for the low permeability, we can see there, we have a comparison in curves from 300 millidarcy, the one on the left, to 3 millidarcy, the one on the right. And we can see that for the lower permeability, we have a higher entry pressure, which makes sense. We need to apply a higher, greater pressure in order to get the entry of the non-wetting phase. And also we can see that for any saturation value, the trend is that we have a lower capillary pressure for the higher permeability samples. So the higher permeability goes lower at the same fixed value, showing that high permeability represents an easier displacement into the pores. And then finally, talking about the relative permeability, just to end with this first section of the static and dynamic properties that we will use in the second part of this course. When we have more than one fluid saturating the porous medium, we have to use the effective permeability. And in this case, it will represent the flow capacity of each phase. Basically, this is very important because when we have more than one phase, all the capillary effects take place, right? As we saw before. So it's not equivalent to have a fully saturated porous medium with one fluid than to have two immiscible fluids, because we will have interactions between them and we have capillary forces there too. So there is an extension of the Darcy law that is used for multi-phase flow, in which we have the flow of the phase related, is the same form of the Darcy law for absolute permeability, but then we will use the flow of the phase, and we will use effective permeability of the rock for that phase, and the viscosity of the phase. And then usually we have the sum of all the effective permeabilities will be equal or lower than the absolute permeability. And why is that? That's because of the capillary effect that we were talking about. So having more than one phase usually reduces the flow capacity of the porous system. So it will have less ability to transfer both fluid together than it will have to transfer only one phase. But what is more useful as a parameter for creating dynamic models is the relative permeability. That is basically the relationship between the effective permeability and the absolute permeability. So we can define this for each phase, and it will be in the range between 0 and 1. Of course, when we have a higher relative permeability, we are saying that that phase has a greater flow capacity. So each flowing condition at which we have a high relative permeability of oil is a favorable condition for the recovery of displacement of oil in the rock. So the relative permeability curves, as I said before, are the most important parameter because they will tell us how much oil flows. And unfortunately, they are not so easy to characterize because they depend on a lot of things. They will be sensitive to pore throat size distributions and pore shapes, but they also will be very sensitive to wettability, as we will see in the second part of this course. They will be completely affected by wettability and viscous to capillary force ratio. And also we have scaling effects, as we know that when we get a pore scale displacement calculations, and if we compare that to plug scale displacement calculations, and we compare that to reservoir scale, the relative permeabilities are not necessarily related. So we need to do some upscaling techniques in order to get to know how to get from one displacement scale to the next one and then to the next one. So for the relative permeability curves, we have they show the flow capacity under the states of saturation. As we can imagine, the relative permeability will depend on how much fluid we have in the porous system. Of course, we will have more capacity of flow of oil when we are at higher oil saturations. And as the saturation of oil decreases, we will have a lower capacity of flow of oil and a greater capacity of flow of water. So that's what we see in the example of the curve there, in which we can see that we have the wetting and non-wetting phase relative permeabilities as a function of water and oil saturation. So in this case, as we see that the wetting phase relative permeability curve increases with within the oil saturation, we can assume some wettability behavior for this in terms of what of oil saturation increasing and wetting phase relative permeability increasing as well. What is important also here is that we have 3 different regions in which we can see that for this, after this critical saturation, we have flow of only one phase. So in this case, for example, we have only flow of oil. That means that we have the saturation. Below the saturation, the water is not movable. So if we, this is the reducible water saturation or the critical water saturation. And in order to have a flow of water, we need to have higher water saturation than this. And then in the other region, we have the opposite effect, in which we have only water flow. So oil has no flowing effect into this part. So then in this intermediate part, there is a transition zone. We will have relative permeabilities within oil and water flow, and both of them are movable. So the measurement of in lab methods are basically part of a special core analysis or SCAL. And the most common lab technique is the core flooding to obtain the relative permeability. So core flooding is basically the injection of different sets of fluids into a core holder that contains a core sample or plug sample. And then we will do displacement in different ways, injecting the fluids in different schemes of injection, depending on the type of test, and measure the recovery and measure the delta pressure also. And with data analysis, we can estimate the saturation by material balance, and we can estimate the relative permeabilities by relating the delta P and the production of each phase. So we have the full experiments. We'll measure saturation and relative permeability points at different saturation points, and we'll match the data, feed the data to get the curve. And then there are the simplified experiments that will only measure the endpoints or the last points at the minimum and maximum saturations. And then with these endpoints, we can use core ELAT splines or other equations to fit the data and to get the shape of the curves. So this is an image of a core flooding experiment. We can see we have the piston cells accumulators for injection of the fluid. We have pressure transducers, and we have the core holder in which we place the plug sample. So talking about the experiment setups, we have a steady state. This is the most accepted steady state technique, but usually it's the most accepted, but isn't the most time consuming and resources consuming because we need to establish a steady state at each step of the experiment. So after the drainage and aging, we start with the core at connate water saturation. So first we will perform the, I didn't put all the previous step of the core preparation involves cleaning the core and then saturating it with brine, measuring the brine permeability. And then we will perform the drainage, displacing the brine with mineral oils, and then finally with the crude oil, and then we will perform the aging to restore the initial wettability. And then at that point, we will have the connate water saturation, and then we'll start injection of oil and brine simultaneously until reaching the steady state. And that means we will have a constant delta P and constant production of water and oil in the outlet. So we will have injection and production at the same rates for each step. So then we will change the rates, the ratio of rates. For example, we'll start with 75% of oil and 25% of brine, and then we will change to 50-50 and then 25-75. And then we can use Darcy's law and material balance to obtain the KR and saturations at each time step. So this is a scheme of what we have in terms of injection and production for each time step, for each step of the experiment. And the thing is that the data analysis is really straightforward for this, but the problem is basically the complexity comes with experiment, because depending on the type of core we have and the fluids, it can take weeks to stabilize each steady state step. So with that, we can have an experiment that can take several months. So this is very time consuming in terms of lab resources and in terms of time. Because we will have the data available really far in time if we think about the SCALP program. So usually the collected data can be used in a plug scale flow simulator to produce and match the curves. And then we have the unsteady state in which we have the same. We start with drainage and aging, and then we will start with the core and SWI. But then we will inject only brine, so it's a water flooding basically, and we will perform measurements of the volume produced as a function of time. So this experiment is much faster because after we do all the aging and the cleaning and the aging, in terms of a week, we can do the whole injection of brine until getting to the final part of the SOR. The thing is that the data analysis, it requires different methods for the data treatment, and it's not so straightforward, and have some assumptions. And there are some companies that actually do not accept the unsteady state for relative permeability calculation. So this, as I said before, for SCAL, there are no standard procedures. Some laboratories, companies, institutes, they have their own procedures, and some of them, they develop their particular procedure for analysis. And then we have the centrifuge, that is a faster experiment, and this is very indirect. We have some calculation methods. I put the reference there, in which we will be recording the effluent as a function of time, as I explained before. If we have the fluid level, we know how much fluid was displaced, and then we have a relationship with spinning with the capillary pressure or with the pressure differential, and with that we can use some methods to treat the data and to get estimation of permeability. So this is simpler and usually faster. It can measure very low relative permeabilities, and also, but then there's a drawback, that is it can measure only the relative permeability for the displaced phase. So if we are displacing water, if we are intruding water and displacing oil, it will measure only the imbibition relative permeability to oil. And if we are displacing water with oil, it will measure the drainage relative permeability to water. And also, when we have gas, there are some compressibility effects and gas diffusion effects. So special care has to be taken when doing this type of centrifuge analysis for gas drain, for imbibition when we have gas water systems. And then, well, to finish up, this is a case study that I brought here. This is from Halliburton. It's a publication at the SPE conference. And it's just to measure, to give an example of a integrated workflow that had a digital rock analysis part and a routine core analysis and SCAL, experimental SCAL together. So they integrated themselves and they compare the times and quality control of the results. So the application is a carbonate formation that had 4 different layers with different permeabilities. And then we have a very tight still light layer that is the second layer there. So the idea here was to perform both physical and digital SCAL and to compare the results. There was whole core scanning was performed, and then the plug selection was carried out, as I explained before. And then micro CT acquisition was performed for the selected plugs at a higher resolution, reaching up to 500 nanometers. And then there were the procedure consisted in doing the capillary pressure curves for drainage, numerical capillary pressure curves from drainage, and then imbibition, relative permeability curves. Those are the digital, and then for the SCAL, we have porous plate capillary pressure for drainage and core flooding steady state imbibition for the relative permeabilities. So here we can see for the 4 layers, that one of the plugs here, we can see that one of these have 2 different plugs. So the third and the 4th layer were plotted together because they were very similar. So we can see that we had simulated using an intermediate wet that was obtained in wettability measurements. And then we can see a very good agreement between the digital rock analysis and the steady state core flooding experiments. We can see that the crossover of the course is very similar in the first and the last layers. So basically, we see a very good agreement between both results. In the result in the middle, we saw that the digital rock analysis obtained plots for intermediate wettability, while the experimental SCAL obtained plots that were more in agreement with oil wettability. We will have a more explanations about how to see these effects in the relative permeability curves in the second part. But then we saw this different behavior, and this was further investigated after this. But in the beginning, we agreed that the digital rock analysis provided reliable results following the intermediate wettability trend. And then on the bottom, we can see upscaling carried out for a composite using the 4 plugs together. So there is no experimental result here because there were no capability to perform an experiment in such a large core as this, such a large plug as this, composite like this. But for this, 2 different wettability scenarios were carried out. So this was another advantage of the digital rock analysis, that was able to perform flow simulations, upscale simulations, considering the 4 layers together in one only unit. So to conclude, there was a time optimization for decision making. So the physical SCAL took 6 years in total, and the digital SCAL took 6 months for this case. So it's important that to say that the digital skull is not a substitute of the physical one, but it is good to have these results faster in order to or do preliminary calculations or perform quality control and make decisions in order to optimize the physical skull. Also, sensitivity analysis was performed by generating wettability scenarios, and it went beyond the scales because we could, the workflow went to downscale up to nano CT resolution and then upscale up to a whole core composite. So with that, that's all that I had for this first part. I tried to focus on these basic concepts in order to give this type of explanations before we move forward to insights in wettability. So I think I will stop sharing my screen because I cannot see the.
So there is, I think, one questions in the chat if you can't read it.
Okay.
I will recopy paste it again.
I see one. I see one that says, can we use the calculated porosity and permeability from MICP to generate a permeability regression instead of the RCAL? And then one says, do you prefer to have a break? That's for me, sorry. Okay, so yeah, so there are ways to do this type of data analysis and regressions. But the thing is, the standard procedures usually, okay, can you hear me?
Yes.
Sorry, I was hearing some background. So for the standard procedure, it's basically the RCAL or RCA or analysis. So for porosity, I would say that we can use the MICP data with more reliability. And then for permeability, we have ways to do regressions to calculate permeability, but these indirect measurements, I will compare this to, for example, calculating permeability from NMR. It will not always be the first choice for many service labs or many operators. The idea is try to build models in terms of physical direct measurements like RCA, but there are methods to do these regressions.
Hi, Doctor.
Hi.
I working on generated the facies model or rock typing model from MICP data. First, I use the routing core analysis data to generate the rock type using Winland and FZI. But when I want to validate the result with MICP data, it is not matched. So I used the MICP data, porosity and permeability as input for Winland and validated. I use it more matched than RCI data. So that's my question. Why I use it MIC data than RCI data?
Yeah, sorry, I lost the last part of your question. You said you used the validation of the MICP, but I couldn't hear the last part that you said.
When I generate a rock typing from using Winland or from routing core analysis data, I need to validate it with MICP data.
Yes.
But it is not matched. So I used the calculated porosity and permeability from MICP to generate the rock type. When I validate it, it is matched with the MICP.
Okay. No, yeah, I understood now. Yes. Okay. So you mean for validation? I didn't understand before. Okay. Yes. Yes. So yeah. Well, in rock typing, it's that sometimes if you get a good match and you get a good validation, I would say this is a good approach. But the thing is that it's very case dependent, right? So that's why I misunderstood your question before, because I thought you were talking more about the general use of the MICP data. So yeah, I agree with that procedure that you are saying, but I think it's specific for each case, right? Case dependent for each type of formation.
Yeah, okay.
I couldn't explain why you wouldn't get a best fit in a best match from the MICP raw data directly.
Because I need optimum MICP curve for each rock type to use it in the model.
Yes.
This is
Okay.
the problem.
Okay, I see.
Okay, so we will take a break. So is there a second, like a second lecture?
Yes, so yes, I have actually a second lecture that is more advanced. So this was, I know for some people, maybe this was kind of basic, but I wanted to give a overall idea of static and dynamic properties. So we have a wettability and rock fluid interaction session after this.
Okay, so perfect. So we will have like 20 minutes.
Okay.
20 minutes break. We will return back here, or 19 minutes. We will return back here at an hour timing, like in 19 minutes. In our timing, it will be 5:10 p.m. Maybe in your time, it's
11:10, yes.
Okay, 11:10. So, okay, we'll return back like in 19 minutes.